Hi, my name is Julian. I'm a PhD student in the ABS lab at CU Boulder, and today I'm talking about reduced order spacecraft charging models. So spacecraft charge naturally in orbit due to various currents, such as the plasma currents to the ambient ion and electron perturbations, but also secondary electron emissions. So as electrons, for example, impact the spacecraft, they excite secondary electrons that leave the spacecraft. So that is an additional current. And also there is the photoelectric effect. So the photons that come from the sun excite electrons in the surface material of the spacecraft, and these electrons leave the spacecraft and therefore also provide a current. These currents depend on various factors such as the plasma environment itself, how many electrons do you have, ions, and what are their energies. The currents also depend on the spacecraft shape and the spacecraft material, for example. And in general, these currents are pretty difficult to model, and maybe even computationally expensive. So in this work, we'll look at how to quickly compute these currents with approximations. So what are the consequences of spacecraft charging? Well, some of the consequences are for an individual spacecraft, for one spacecraft itself. So um, spacecraft charging could cause damage to onboard electronics, but also interference with scientific measurements. In our lab, we're more focused on the consequences between two spacecraft that are charged. And some of those effects are, for example, an electrostatic discharge between the two spacecraft if the electric potential is different between those two spacecraft. And especially what we're interested in are the electrostatic forces and torques. So if you have two spacecraft that are charged and in close proximity, they exert forces and torques on each other that can perturb the relative motion between those two spacecraft, and also can cause an uncooperative target or uncooperative spacecraft to start tumbling. In general, we refer to this area of research as charged astrodynamics. So, what are the consequences on orbit servicing? So, if you have, let's say, an uncooperative target object that you're trying to service with a servicing satellite, and you come in, the resulting electrostatic torques will cause the uncooperative target object or target satellite to start tumbling. And as a result, if you want to maintain a constant relative orientation between your servicer and the target, you will have to translate around the target object in order to maintain that constant orientation, for example. So if you're trying to dock, for example, and the target starts rotating or tumbling away, then you will have to follow that orientation with your servicer. And another consequence or area of research for these electrostatic forces is the electrostatic tractor. So the electrostatic tractor has been proposed to remove space debris from geostationary orbit touchlessly using an electron beam. So you have a servicing satellite equipped with an electron gun, and that electron gun is aimed at the debris in geostationary orbit. And as a result, the servicing satellite emits electrons with the electron gun, so it charges positively, but the electrons are accumulating on the debris, so the debris or the retired satellite charges negatively, and that results in a attractive electrostatic force that can be used to relocate that debris. So now let's get into spacecraft charging models. What can we do here, and what are the simple models, and what models are a little bit more complicated but more accurate? So for the force model, the simplest case is to consider two spheres, so one sphere per spacecraft. A more advanced approach that was developed a few years ago is the so-called multi-sphere model. So in that case, you use a lot of spheres to better represent the actual shape and charge distribution of a spacecraft, of a complex shape, basically. Now, for the charging model itself, so where we model the the currents that act on the spacecraft, a lot of work so far has considered spherical spacecraft. But a more accurate representation would be a faceted model where you divide the spacecraft area into facets, and therefore you have a better approximation of, first of all, the total surface area, and second of all, the area of the spacecraft that is actually facing the sun, for example. So you have an orientation dependent sun facing area in this case. So for the multisphere method, we use, as I mentioned before, a number or a large number of spheres to represent the spacecraft shape, and using those spheres and assuming that we know the potential of the spacecraft, we can solve for the approximate charge distribution of the spacecraft, and then we compute the electrostatic force between each sphere on the two spacecraft, and then we get the total force and torque by summing up all these forces and torques. For the faceted model, we divide these the spacecraft surface into several smaller facets, and using the normal vectors of those facets, we can compute the total surface area of the spacecraft that is facing the sun at that moment. And with that, we can compute the photoelectric current shown on the bottom left. That will be, if we use a faceted model, it will depend on the orientation of the spacecraft itself. So on this slide, I'm showing how much the equilibrium potential of the spacecraft can vary if we change the orientation of the spacecraft. So we use yaw and pitch angle to change the orientation of the spacecraft, and then considering the plasma currents, the secondary electron emission, and the photoelectric current, and the electron beam current due to a servicing satellite, we compute the equilibrium potential. And as we can see, there are huge differences depending on the orientation. So if you, for most orientations, the equilibrium potential is around 0 volts. But for example, if we have a yaw angle of 0 degrees, and then for all pitch angles, basically, the equilibrium potential is strongly negative, so about negative 10 kilovolts in this case. And that is because for that specific orientation, the solar panel is not facing the sun. So as a result, the total surface area of the spacecraft that is facing the sun is much less. So we have less of a positive photoelectric current acting on the spacecraft. So the total current from the total sum of all currents is more negative, and we get a negative equilibrium potential here. For the other orientations, the solar panel is in some way or another facing the sun, so we have a stronger photoelectric positive current, and as a result, the equilibrium potential is close to 0. And the equilibrium potential also affects the force and torque that acts on the spacecraft, on the debris, for example. So on the left, we see how the force varies with orientation, and on the right, we see how the torque varies with orientation. And for that comparison, we use 4 different models. So we have what will be, in this case, the highest fidelity model, that is the faceted model, to compute the currents, and using the multisphere model to compute the forces and the torques. And then we have the simplest model, which uses a spherical assumption to compute the currents and uses 1 sphere per spacecraft to compute the currents. And then 2 different models in the middle that have either a spherical assumption to compute the currents and a multisphere model to compute the current, the forces, or the other way around. And what we see here is that first of all, the spherical, so the simplest model where we have the spherical assumption and use one sphere per spacecraft to compute the force, there is no variation in force over over any orientation. If we use the faceted model to compute the currents, but a one sphere model for the forces, then we have the red surface, which is in the end really similar to the graph shown here for the potential, because the potential has a direct effect on the force. Now for the multisphere model plots here, we have another variation, and that is due to the orientation of the spacecraft itself. So for example, if the solar panel is directed towards the servicing satellite, so if the solar panel of the debris shown on the left is facing or pointed at the servicing satellite, then we have a stronger force. And that's what we see here with the yellow and the blue surfaces that have spikes for those or peaks for those corresponding orientations. For the torques on the right side, if we use a one sphere model to compute the force and torque, we have no torque at all, because in our assumption the center of the sphere aligns with the center of mass of the spacecraft, and since the electrostatic force acts on the center of the sphere, there is no leverage to cause a torque. And for the multisphere model, we have a orientation dependent torque, and that torque is emphasized if we use a faceted model to actually compute the electric potential. And as a result, what I'm showing here is a simulation of the electrostatic tractor debris removal process in geostationary orbit, where the two spacecraft are separated by 15 meters. And then for 3 hours, the servicing satellite is tugging the debris using those electrostatic attractive forces. Now, again, we use the four models as on the previous slide. And some of those models are, especially the spherical assumption one sphere model, is unable to compute a orientation dependent force or torque, and as a result the orientation or the angular velocity of the spacecraft in the bottom plot remains constant, and therefore the force, since the orientation doesn't change, the force and the potential remain the same throughout the simulation as well. In our highest fidelity model, in the faceted model and using a multisphere method to compute the forces, we have really high variations in both the electric potential as well as the corresponding or resulting electrostatic force. That is shown by the solid red line. And these, since the potential, for example, drops to zeros at some times, the corresponding or the resulting electrostatic force will decrease in magnitude a lot as well, and that can result in longer reorbit times than expected, because the reorbit time depends on how strong the force is between those two, between the two spacecraft. The stronger the force, the faster we can reorbit the debris. But if the force is weaker, then we take longer to reorbit the debris. So in conclusion, the effective sphere model to compute currents, so where we use a spherical assumption, cannot match or might not match the truth model well in terms of total surface area. And in addition to that, the area of the spacecraft that is facing the sun is constant throughout all times or orientation. With a faceted model, on the other hand, we can approximate the total surface area of the spacecraft better, and we have a time varying or orientation varying area of the spacecraft that is facing the sun, which allows us to have more accurate simulations, because the area that's facing the sun affects the equilibrium potential of the spacecraft, and that equilibrium potential again affects the corresponding electrostatic force and torque, and therefore this will affect any simulations that deal with electrostatic forces. Thank you very much for your interest in this work. Kaylee and I would like to thank NASA for supporting this research, and please feel free to reach out if you have any questions.